Well, hi everyone, this is Bob the Science Guy. I'm going to continue my review of University Physics with University Physics 2. Chapter 1 is going to be heat and temperature. So let's get right into it. This is University Physics 2, but it also applies to college physics. The difference between university and college physics is really just the mathematics. College physics uses algebra and trigonometry. University physics uses algebra, trigonometry, and calculus. Now, chapter 1 talks about thermodynamics and thermal equilibrium. So let's go ahead and just talk a little bit about what heat is. Heat is the average kinetic energy of a substance. And heat is transferred from one substance to another if they are of different temperatures. So for example, if block A is 300 Kelvin and block C is 250 Kelvin, what will happen is heat energy will transfer from block A, the hotter block, to the cooler block, block C. When both block A and block C are the same temperature, which is what is read off of a thermometer based on various scales, but if they are of equal temperature, they are said to be in thermal equilibrium. If they initially are not in thermal equilibrium, the hot object will transfer heat to the cooler object until they are. Now, another thing that you may hear about as well is something called the zeroth law of thermodynamics. What the zeroth law says is very, very simple. If block A is in thermal equilibrium with block B, and block C is in thermal equilibrium with block B, the zeroth law says that block A will also be in thermal equilibrium with block C. Now there are three temperature scales in common use. We have the Kelvin scale, we have the Celsius scale, and we have the Fahrenheit scale. The Kelvin scale starts off at 0 Kelvin, which is absolute zero, and it only gives indications in the positive direction. Absolute zero is the coldest that an object can get. All of the molecules stop moving, and it has no more kinetic energy. The freezing point of water on the Kelvin scale is 273.15 Kelvin. Not degrees Kelvin, just Kelvin. In many classes, you'll see this abbreviated to just 273. And the boiling point of water is 100 degrees higher. The only difference is where the freezing point of water is, and that's 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. Notice it's also a value of 100 different between the freezing point in Kelvin and the boiling point in Kelvin. That's because the degrees are the same increment. And then finally we have the Fahrenheit scale. The freezing point of water is 32 degrees Fahrenheit, and the boiling point is 212 degrees Fahrenheit. Now these two scales are both dependent on pressure. The Kelvin scale is dependent on something called the triple point. Now the conversion between Celsius and Kelvin is pretty straightforward. You take the degrees Celsius and add 273.15, and that will equal Kelvin. Likewise, if you have Kelvin, you subtract 273.15 and you get the temperature in Celsius. Now remember, this is Celsius, not centigrade. Centigrade just means 100 increments. Celsius is the actual scale. Now the conversion of Celsius to Fahrenheit is a little trickier. You take the degrees Celsius, you multiply them by 9/5, and then you add 32, and that will give you the temperature in Fahrenheit, well, degrees Fahrenheit. Remember, notice that Celsius and Fahrenheit have degrees. Kelvin is just Kelvin, K. Now to convert from Fahrenheit back to Celsius, you just reverse the process. You subtract 32, and you multiply by 5/9, and you end up with degrees Celsius. When you have two objects, a hot object and a cold object, heat can be transferred between them in three basic ways. They can either be touching, and that is called conduction. It is direct transmission of heat from one object to the other. An example of that would be a cold egg in a hot frying pan. If you were to put a hot object near a cold object and let the heat transfer through the air between them by heating up the air near the hot object and having that warm the cooler object. That would be using something called convection. And this is the way a standard oven works. You have a heating element, it heats up the air in the oven, and that's what cooks the turkey. A third way is through radiant heat. And radiant heat, a good example of that is the sun. You have the hot sun and the cold earth, and heat is transferred from the hot sun to the cold earth by means of electromagnetic radiation. An example of this would be an infrared heat lamp. The food is not touching the lamp itself, and the lamp isn't so much raising the temperature of the air, but the infrared radiation coming off that hot lamp is heating up the cold food. Now in the next part of the chapter, we're going to talk about thermal expansion. This is very important when dealing with roadways and bridges and things like that. As you heat an object up, it tends to lengthen, and if you cool it down, it tends to contract. So we'll learn how to calculate that in the next segment. Take care.